The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, okay, so it's Laplace again today, Laplace's equation. And I wrote, trying to describe, that's a big area that a lot of people have worked on for centuries. And for the early centuries, they were always analysis methods. And that's what we got started on last time, and we'll do a bit more. There's no way we could do everything that people have worked on years and years trying to find ideas about solving. But we can get the idea. And this part then is in the section called Laplace's equation. And the exam Wednesday would include some of these constructions, right? So this is what we did last time. We identified a whole family of solutions to Laplace's equation as polynomials in x and y of increasing degree n. And then when we wrote them in polar form, they were fantastic. R to the nth cos n theta and r to the nth sine n theta. So my idea is just, we've got them, now let's use them. So how to use these solutions. Because we can take combinations of them, we can create series of sines and cosines. So I'll do that first. Series. And then Green's function, that's the name. You remember we've seen it before. That's the solution when the right side is a delta function, when we have Poisson's equation with a delta there. So that's an important one. And then, a big part of two-dimensional and three-dimensional problems is that the region itself, not just the equation, but the region itself can be all over the place. We'll solve when the region is nice, like a circle or a square. And then there's a way to, in principle, to get other regions, to change from a crazy region to a circle or a square and then solve it there. So that's called conformal mapping. And I can't let the whole course go without saying a word or two about that. But somehow, among numerical methods, it's conformal mapping. There are packages that do conformal mapping, but they're not the central way to solve these equations numerically. Finite differences, finite elements are, and that's what's coming next week. Yeah, so this is the future. This is the present right there. Okay. So can I just start with an example or two? Like, how would you solve Laplace's equation in a circle? So in a circle. So this is the idea here. I have Laplace's equation. Okay. So I've got a whole lot of solutions. And I've even got chalk to write them down with. Okay. So here's my circle. Might as well make it the unit circle. Radius 1. And inside here is Laplace. uxx plus uyy equals 0. No sources inside. So we have to have sources from somewhere, and they will come from the boundary. So on the boundary, we keep let me think of u as temperature for the moment. So I set the temperature on the boundary. U equals some u0, some known function. This is given. This is the boundary condition. This is the given boundary condition. And it's a function of, I'm going to use polar coordinates. Polar coordinates are natural for a circle. So this is at r equal 1. So this is, maybe I should say, on the boundary, which is r equal 1, and going around the angle theta is given. is this u naught of theta. That's my given boundary conditions. This problem is named after Dirichlet, because it's like giving fixed conditions and not Neumann conditions. Okay, so I'm just looking for a combination for a function that solves Laplace's equation inside the circle and takes on some values around the boundary. And of course, the boundary values might be +1 on the top and -1 on the bottom. Or the boundary condition might vary around, it might variable and come around, but notice that this is a periodic function. This is 2 pi periodic, because the problem's the same. If I increase theta by 2 pi, I've come back to the same point, so it's got to have that value. Okay, so, well, let me give you a couple of examples first. Suppose this function, example 1, easy. Suppose u0 is sine 3 theta. Okay? So that means I've got a region here. I'm prescribing its temperature on the boundary, and I want to say, what does it look like inside? And I'm prescribing right now the sine 3 theta, so there's theta is 0, so it's 0, the boundary condition 0 there, climbs to 1, back to 0, back down to -1, back to 0, 3 times, and comes back to 0 again there. So I'm looking for a solution to Laplace's equation, and I've got a pretty good list that will match u0 when r is 1. So that's the boundary. R is 1. So you can tell me what it is. So you can solve this problem right away. The answer is u of r and theta is what function will, remember, I've got my eye on that list. You too, right? I'm just trying to get one that when r is 1, it will match sine 3 theta. What's the good guy? It'll be on that list. Which of those by itself? Here I don't need a series because I've got such a neat u0 function. I'll get it right with one answer. And what is that answer? I look there, I say, what do I do so that at r equals 1, I'll match sine 3 theta? Well, I'll use r cubed sine 3 theta. So the good winner will be r cubed sine 3 theta. That solves Laplace's equation. We checked it out. It's the imaginary part of x plus iy cubed. We could write it in x and y coordinates if we wanted, but we don't want to. And it matches when r is 1. It gives us sine 3 theta. That's it. Okay. So let's see. And of course, I could take any one. Now suppose I'm trying to match something that's not as simple as sine 3 theta. In that case, I may have to use all of them, right? I mean, it's very, very fluky that one term is going to do it. Usually, so my main examples would be I'll have to match all of them. So what do? At r equal 1, so my general solution has this nice, is a combination of these guys that I worked so hard to get. The solution is of this form. It's some a naught, the constant, and then an a1 r cos theta, and a b1 r sine theta, and a a2 r squared cos 2 theta, and so on. You see what? I'm just taking any combination of, I'm using the a's as the coefficients for the cosine guys, and the b's, b1, b2, b3 would be the coefficients for the sine ones. Okay, that's my general solution. That solves Laplace's equation. Every term did, so every combination will. Now set r equal 1 to match, set r equal 1 and match the boundary, and match u0 of theta, the required temperature around the boundary, on the boundary being where r is 1. Okay, so I said set r equal 1. So then u0 of theta, this given thing, has to match this when r is 1. So it's a0 plus a1. Now what do I write here? R is 1, so it's just cos theta. Now b1, r is 1, so I just have sine theta. Then I have an a2 cos 2 theta, and a b2 sine 2 theta, and so on. That's, here, just let me put it together now. I'm given any temperature distribution around the boundary. It's in equilibrium. The temperature, you know, where if the temperature is high near that point, then and low over here, the temperature inside will gradually go from that high point to the lower one by matching on the boundary. And this is the match on the boundary. Now, this is really a lead-in to the last part of this course. Do you know, so whose name is associated with a series like that? Fourier. You recognize that as what's called a Fourier series. So the idea is I'm given these boundary values. I find their expansion in sines and cosines, and that's what we'll do in November. And then I've got it. Then I know the A's and the B's. And then basically I just put in the R's, R and R squareds and R cubes and so on, so that then I've got the answer inside. In principle, it's so easy. You know, this looks, well, so why is it easy, though? First, it's easy because it's a circle we're working in. If I was in an ellipse or a strange shape, forget it, right? I mean, so this is quite special. And secondly, it's easy because these functions are so nice that they will allow, that's, you know, Fourier works with the best functions ever, these sines and cosines. So they will, I'll find a way to find those coefficients, the A's and the B's, that even though there are lots of them, I'll be able to pick them off one at a time, the A's and B's, and then once I know the A's and B's, I know the answer. So do you see, this is in principle a great way to solve it. In fact, it's the way we used over here. When my u0 was sine 3 theta, then the only term in its Fourier series was 1 sine 3 theta, and then the solution was r1 r cubed sine 3 theta. Yeah, so that you can learn things from this. For example, what can you learn? One thing I noticed, these is an important feature of Laplace's equation is that the solution inside the circle gets very smooth. We could have a very, the u0, the boundary conditions could be like a delta function. I could say that on the boundary, the temperature is 0 everywhere, except at that point it spikes. So I could take u0, so example 2, and I won't do it in full, would be u0 on the boundary equal a delta function. A spike at that one point. So it's all the heat is coming from the source at that one point. Like I've got a fire going there. I'm keeping the rest of the boundary frozen, and the heat's kind of going to come inside. So then how would I proceed? Well, if I have this boundary value as a delta function, I look for its Fourier series. And it's a very important, beautiful Fourier series for a delta function. Would you want to know it? I mean, we'll know it well in November. Would you want to know it in October? This is Halloween, I guess, so we put so delta, I'll tell you what it is, since you insist. Delta theta, I think, well, I think there's a 1 over 2 pi or something. Shoot, we'll get it exactly right. It's something like 1 and 2 cos theta and 2 cos 2 theta. I'm not sure about the 2 pi. 2 cos 2 theta and 2 cos 3 theta and so on. We'll know it well when we get there. What I notice about this delta function, of course, you're going to expect the delta function to be somehow a little bit strange. At theta equals 0, what does that series add up to? Just to begin to get a hang of Fourier series. At theta equals 0, what does that series look like? Well, all these cosine thetas are 1. So this series at theta equals 0 is 1 plus 2 plus 2 plus 2 plus 2. It's infinite. And that's what we want. It's that the delta function is infinite at theta equals 0. And it's periodic, of course, so that if I go around to theta equal 2 pi, I'll come back to 0 again. At theta equal pi, you could sort of see, well, yeah, theta equal pi is a sort of interesting point. At theta is pi, what's the cosine? Is -1, right? But then the cosine of 2 pi will be +1. So at theta equal pi, I think I'm getting a 1 minus a 2 plus a 2 minus a 2 plus a 2. You see, it's doing its best to cancel itself out and give me the 0 that I want at theta equal pi over on the left side of the circle. Anyway, suppose that's an extreme example. But now, what's the temperature inside? Can you just follow the same rule? What will be the temperature inside? If that's the delta function, if that's the right series, whatever, it might be a 4 pi, I'm not sure, for that. Now, you can tell me what's the solution, what's the temperature distribution inside a circle when one point on the boundary is held at, has a heat source, a delta function. What do I do? How do I match this with this guy? I just put in the r's, right? If this is what it's supposed to match when r is 1, then when r is, so I don't know where maybe I'll put it under here. So the u of r and theta from the delta guy is just put in the r's. 1 plus 2r cos theta and 2r squared cos 2 theta and so on. Okay. And eventually 2r to the 100th cosine of 100 theta and more. Okay. I write this out. You could say, why did he write this down? I wanted to make this point that the important feature of the solution to Laplace's equation is how smooth it gets when you go inside the region. And why is that? Because if at r equal a half, this term is practically gone, right? At r, if I go halfway into the circle, this term is practically gone, 1/2 to the 100th power. And if I go to the center of the circle, it's completely gone. In fact, what's the value at the center of the circle? What's the temperature at the center? Is what? 1 over 2 pi. This is the only term that's remaining. And it's the average around the circle. That makes physical sense, I guess. Since the whole thing's completely isotropic, that we've got a perfect circle. If we have, if our boundary value, the value at the center of the circle is always the average going around. The constant term in the Fourier series, this guy, we'll get to know that one very well. That's the average. You're just seeing a little bit of Fourier series early here. But my point is that you could have high oscillation around the boundary. That damps out because of these powers of R. And inside the circle, it's only the low order terms that begin to take over. Okay, so I did. You see how Laplace's equation, this is the kind of trick you have, or not trick, but the kind of method that you can use for solving Laplace's equation by an infinite series. Of course, a person who wants a number can complain that, wait a minute, how do I use that infinite series? Well, of course, you would have to plug in, if you wanted to know the temperature at a particular point, you'd have to plug in that value of R, that value of theta, add up the terms until you hope that they become so small that you can ignore them. Yeah, but so infinite series is one form of a solution. And I could, somehow these are examples. I should use the words separation of variables. Separation of variables is the golden idea in this analysis stuff. Separation of variables means I got the R part separated from the theta part. And that worked great, worked well for a circle. Let's see, maybe for a square I could try to separate x from y. Maybe there's a homework problem. Another solution a solution that separates x from y, I think, is something like, so this would be another family, good for squares, something like sine kx sinh times, so this separation is something in x times something in y. I'm just mentioning things. I think that solves Laplace's equation, because if I take two x derivatives, that'll bring down k squared, but it'll flip the sign, right? It's two derivatives of the sign will be a minus. And if I take I need a ky there. And if I took two derivatives of this hyperbolic sign, this you remember that's the e to the ky and the e to the minus ky. The two derivatives of that will bring out a k squared with a plus sign. So two x derivatives bring out the minus k squared, two y derivatives bring out the plus k squared, and together that solves Laplace's equation, I think you just will check that in a homework problem. So there would be an example, good for a square. There's hope to do an exact solution in a special region. Now, what's this Green's function idea? What's the Green's function idea? Okay, yeah, this is another thing. Okay. So last time we appreciated that this combination x plus iy was magic. The idea was that we could take any function of x plus iy, and it solves Laplace's equation. Can we just see sort of very crudely why that is? we saw the pattern. We saw it. We saw x plus iy to the nth. Sort of we went as far as n equals 3, checked it all out. But now, really, if I want to be able to, why does that solve Laplace's equation for any n? Maybe, should I just plug that into Laplace's equation? What happens if I take the 2x derivatives of this thing? So this is to be a typical function of x plus iy, typically nice one. If I take 2x derivatives, I'm going to plug it in and see that it really does solve Laplace's equation. So 2x derivatives of that will give me what? The first x derivative will bring down a n times this thing to the n minus 1. And then the next x derivative will bring down an n minus 1 times this thing to the n minus 2. So that'll be the uxx stuff, right? And what about uyy? This is my u. I'm sort of just checking that, yes, this seeing again, see if it still works Friday, what worked Wednesday. That this x plus iy is magic, and functions of it like powers, exponentials, logarithms, whatever, all solve Laplace's equation. Okay, so we did uxx, and we got easy. Now what happens with uyy? Do you see the point? Sorry? Opposite sign. And why does the sign come out opposite? Because of that guy. Yeah, it's the chain rule, right? The derivative of this with respect to y will give me an n times this thing to one lower power times the derivative of what's inside. And the derivative of what's inside is an I. And then the second derivative will bring down an n minus 1. This guy will be down to n minus 2. Another I will come out. And just what you want, right? Because the I squared is minus 1. Those cancel when those are equal opposite sign. And we get uxx plus uyy equaling 0. So that works. And actually, the same idea would work for any function of x plus iy. The two x derivatives just give f double prime. Two y derivatives will give f double prime, but the chain rule will bring out I both times, and we've got it. Okay, so, well, I think we just need another couple of examples. And this, of course, could be in polar coordinates f of r e to the I theta. Everybody recognizes r e to the I theta is the same as x plus iy. Better just be sure we've got that. X is some point here in the complex plane. Iy takes us up to here. So there's x plus iy. That's x plus iy there. But it's also, so here's, yeah, let me put those in better. And there's x and there's y. And yeah, everybody knows this picture, right? That this x and this y, now if I want to go to polar coordinates, that angle is theta. This x is r cos theta. This y is r sine theta. And this guy is r e to the I theta. R e to the I theta. R cos theta plus I, r sine theta, is the same as r e to the I theta. That's utterly fundamental. Everybody's responsible for that picture of putting the complex numbers into their beautiful polar form. That's what made our r to the nth cos n theta all so simple. Now, what was I aiming to do? Give a particular f. Now I want to give a particular function f, and or maybe a couple of choices. A couple of functions f, and see that their real parts and their imaginary parts solve Laplace's equation. Yeah, what shall I do? Let me take first a really one that works completely. Try take the real part and the imaginary part. Yeah, let me take e to the x plus iy. It's a function of x plus iy, extremely nice function of x and plus iy, and we can figure out its real and imaginary parts, and we get two solutions to Laplace's equation. Because the good way is to write this thing as e to the x times e to the iy. And again, we'll write it as e to the x times cos y plus I sine y. So now I can see that the real part, I can see what the real part is, and I can see what the imaginary part is. The real part will be that's real, and that's real. So this will give me e to the x cos y. And the imaginary part will be the e to the x sine y. You see, and those will solve Laplace's equation. Can I give a name to these? This whole field of analysis. This e to the z is called an analytic. I should just use that word, an analytic function. And these guys, the real and imaginary parts, are two harmonic functions. Maybe it's not so important to know the word harmonic function, but analytic function, yeah, I would say that's an important word. Actually, what does it mean? It's a function of z. So we're doing complex. We're in the complex plane here now. It's a function of z, e to the z, and it can be written as a power series, of course, 1 plus z plus 1 over 2 factorial z squared and all those guys. So it has a power series. That makes it a combination of our special ones. And the great thing about that series is it converges. So an analytic function is the sum of a power series that converges. And this one does. So there's an example. Yeah. So the whole theory of analytic functions is, actually, that's chapter 5 of the textbook. And we won't get beyond this point, I think, in one semester with analytic functions. So what am I saying, though? I'm saying that the theory of analytic functions is closely tied to Laplace's equation, because the real and the imaginary parts give me this pair u and s that they each satisfy Laplace's equation, and they're connected by the Cauchy-Riemann equations. It's a lot of mathematics coming real fast here. Now, I'd like to take one more example. Instead of the exponential, can we take the logarithm? I want to take the log of x plus iy, and I want you to split it into its real and imaginary parts and get the u and the s that go with that. So this was like the nicest possible. We got a series, the e to the z is good for every z. The series converges. Fantastic. It's an analytic function everywhere. Best possible. Now we go to one that's not best possible, but nevertheless highly valuable. Okay, so e to the z I've done. Let me erase e to the z. Take log z. Okay, so now I'm not doing e to the z anymore. And I want to find the logarithm. Okay, so what's the deal with the logarithm? Real and imaginary part. Now I'm going to take the log of x plus iy. That is a function of x plus iy. So except at one point it has a problem, right? There's a point where that isn't, this is not going to be analytic, and there's going to be a special point in the flow which is singular somehow. But away from that point, we have a nice looking function, the logarithm of x plus I, y, and now I'd like to get its real and imaginary parts. I'd like to know the u and the s. Now, but nobody in their right mind wants to take the logarithm of a sum, right? That's a very foolish thing to try to do, the log of a sum. What's the good way to get somewhere with this real and imaginary part? I can take the log of a product. So the polar is way better again. I want to take this, I want to write this as the log of r e to the, I want to write it that way. And now, what's the log of a product? The sum of the two pieces. So I have log r. And what's the log, and the log of e to the I theta, which is I theta. Boy, look, this is fantastic. Fantastic except at 0. Yeah, I mean, it's fantastic, but it's got a big problem at 0. But it's an extremely important example. So what's the real part? It's sitting there. This is my u. This is my u of r theta, my u of xy, whatever you want, is the log of r. The square root of x squared, the log of the square root of x squared plus y squared. This is, let me just put it, I claim that, again, by this magic combination, this r is the square root of x squared plus y squared. I claim if you substitute that into Laplace's equation, you get 0. It works. And what's the imaginary part? The twin is the imaginary part, which is theta. Oh, what is theta in x? If I wanted it in x and y, what would theta be? It's the arctan, it's the angle whose tangent is something. Y over x, yeah, so if I really want it in rectangular xy stuff, it's the angle whose tangent is y over x. And again, if you remember in calculus how to take derivatives of this thing and you plug it into Laplace's equation, you get 0. It works. So that's a great solution, except where? At 0. Except at 0. And this tells us, this doesn't tell us like what's happening at 0. It's a excellent solution. What's the picture? So part of by Wednesday's exam, like I'm not expecting you to be an expert on the theory of analytic functions. I don't expect you to know anything, any conformal mappings by Wednesday. God, but I do expect you to have these pictures in mind. So when I draw those axes, what picture is it I'm planning on? I'm planning on the equipotentials, u equal constant, and who are the other guys? The streamlines. The places where the stream function. So here's the potential function. So what are the equipotential curves for that guy? Circles. This is a constant when r is a constant. So the equipotential functions would be circles. I don't want to draw that circle with radius 0, though. I'm nervous about that one. But all the others are great. And what are the streamlines now? The streamlines are the well, you can, what will the streamlines be? You can, if I've drawn one family, you can tell me the other family. the streamlines will be radial lines, because they're going to be perpendicular to this. And so what do I get? This is the stream function, theta. So what's a streamline? The stream function should be a constant. Theta is a constant. That means I'm going out on rays. Those are all streamlines. Again, everything fantastic. If you look in a little region here, you see just a beautiful picture of equipotentials and streamlines crossing them at right angles. Everything great. Just that point is obviously a problem. Now, and I'm suspecting that there's a source here. I think this flow, which is given by these guys, comes from some kind of a delta function right there, and the flow goes outwards. And we know, so I know u, I know v is the gradient of u, right? I could take the x and y derivatives. I'd know the velocity. I know the stream function. The divergence would be 0. Everything great except at the origin. I think we've got some action at the origin, because if there was no, here's the way to test it. I want to see what's happening at the origin, and I'm going to use the divergence theorem. I'm going to use the divergence theorem. So the divergence theorem says, what is the divergence theorem? So this is the key thing that connects double integrals. Let me take a circle of radius r. So that's the circle of radius r. R could be big or little. So I take this, integrate over the circle of radius r. So what's the deal? V is the same as w. What does the divergence theorem tell me? It tells me that if I integrate, what do I integrate? The divergence of w dx dy, or r dr d theta, then I get the same, I get the flux. This is a key identity. Fundamentally, I mean, more than just a key identity, it's central here. The total flow out of the region must make it through the boundary. So I integrate this boundary, and this boundary is a circle of radius r. And what do I integrate along that circle? What's the other side of the divergence theorem? W dot n. W dot n around the boundary. Okay. And remember, I have this nice, my curve here is this nice circle. So I'm going to integrate around that circle. First of all, what is n? N is the normal. N is, by definition, n is the norm that points outwards, straight out. So it's actually going out that way, right? Yeah. At every point, it's pointing straight out. And ds, I think we can figure out exactly what that right-hand side is. Because, how do I get that right-hand side? I'm looking for w, and then I have to integrate. Okay. Here's my u, log r. Plus, my u is log r. So what's the gradient of log r? It points outwards, And how large is the derivative? So the gradient, the derivative of this log r is 1 over r. I think that this comes down to, this is the integral around the circle. I think that this thing is 1 over r, right? I went pretty quickly there, so I'll ask you to look in the book, because this is such an important example. It's done there in more detail. So I'm claiming that the derivative is 1 over r and that it points directly out. So the gradient points out, the normal points out, so that I just get exactly 1 over r. Now, what is ds? For integrating around a circle. What's a little tiny piece of arc on a circle of radius r? R d theta. Good man. R d theta. Now that's an integral I can do, right? And what do I get? 2 pi. R cancels r. I'm integrating d theta around from 0 to 2 pi. The answer is 2 pi. So what do I learn from that? I learned that somehow this source in the inside has strength 2 pi. What's sitting in there is 2 pi times a delta function. This is the solution to Laplace's equation, except at that source term. So I really should say Poisson's equation. This has turned out to be the solution to Poisson with a delta, or with 2 pi times a delta. We have just solved this important equation, the Poisson's equation with a point source. And of course, that's important because when you can solve with a point source, you can put together all sorts of sources. So, and this is called the Green's function. The Green's function is the solution when the source is a delta. So if I divide by 2 pi, now I've got it. I divide this by 2 pi, and there is the Green's function. I have to put that in bold letters. Green's function. It's the solution to the equation when the source is a delta, and the answer is u is the log of r over 2 pi. So that's the Green's function in 2D. Physicists, you know, they live and die with these Green functions, live, let's say, with Green's functions. And they would want to know the Green's function in 3D. So the Green's function in 3 dimensions, it also turns out beautifully. This is in, they would say, in free space. This is the Green's function when there are no other charges. Nothing is happening except for the charge right at the center. And if I'm in 2 dimensions, it's the Green's function is this log r, so it grows more slowly. It behaves like log r. And in 3D, I think the answer is 1 over 4 pi r. It's just amazing that those Green's functions, when the right side is a delta, have such nice formulas. Okay. Let me take one moment here, because I'm not going to get I'll tell you what conformal mapping is about. But what's your take-home from this lecture? Your take-home is 2 methods that we can really use to get a formula for the answer. One method was for Laplace's equation in a circle. get the boundary conditions in a series of sines and cosines and then just put in the r's that we need. That's a simple method, provided we can get started with the Fourier series. The second method is look at functions of x plus I, y, and try to pick one that matches your problem. And if your problem has a point source at the origin, we found the one. So the literature for hundreds of years is aimed at solving other problems. If the point source is somewhere else, what happens? That's not hard. If it's not a point source but some other kind of source, or if the region is not a circle. Can I say in one final sentence just what to do, this conformal mapping idea, when the region is not a circle? Well, I can say it in one word, make it a circle. I mean, that's what Riemann said you could do it. You could think of a function. So Riemann said that there's always some function of x plus I, y. Let me call this Riemann's function, capital F of x, y. So this is now the idea of conformal mapping. Change variables. Conformal mapping is a change of variable. He picks some function and let its real part be x and let its imaginary part be y, capital Y. Okay, this is totally ridiculous to put conformal mapping in 30 seconds, but never mind. Let's just do it. And the book describes conformal mappings, and classical applied math courses do much more with conformal mappings. But the truth is, computationally, they're not anything like as much used as these. So what's the idea? The idea is to find a neat function of x plus I, y so that your crazy boundary becomes a circle in the capital X, capital Y variables. So you're mapping the region, ellipse, whatever it looks like, by changing from little x, little y, where it was an ellipse, to capital X, capital Y, where it's a circle. And the point is, Laplace's equation stays Laplace's equation. That change of variables does not mess up Laplace's equation. So that then you've got it in a circle, you solve it in a circle for these guys, and then you go back. In a word, you're able to solve Laplace's equation in this crazy region because you never leave the magic x plus I, y. You find a combination with that magic x plus I, y that makes your region into a circle. In the circle, we now know how to use capital X plus I, capital Y. You're staying with that magic combination and getting the region to be what you like. So people know a lot of these conformal mappings. A famous one is the Joukowsky one that takes something that looks very like an airfoil, and you can get a circle out of it. So I'll put down Joukowsky's name. So that's one that I trust, course 16. Still finds valuable. It's a transformation that takes certain shapes, and they include shapes that look like airfoils, and produces circles. Okay, so sorry about such a quick presentation of such a basic subject. Conformal mapping, not on any exam, that'd be impossible. It's really this stuff that you're #1 responsible for.